multiplication delta, and we define the left invariant vector fields or derivations on G to be the derivations of A for which we have this law. Okay, this corresponds to the diagram. To this diagram here. Yeah.
And what we said privately with Elias last time is that this notation is exactly what we expect it to be, in the sense that there is a natural action of G on the derivations, and this weird condition is the translation of what you would expect invariant to mean, right? So invariant means that G acts trivially on these, but this condition is written in terms of the coaction of the coordinate. So it is indeed invariant, and the notation makes sense. It's like the invariance of the action of G, it's just a condition of invariance is written in terms of the co-multiplication of the coordinate ring, not the actual action of G.
Yeah. And this is a restricted Lie subalgebra of the derivations of A. So, the first basic central, I would say, result. This is proposition 1, 4, 12 in Lyon. Is that this thing is actually isomorphic to the tangent space at the identity. Via the evaluation map at the identity. So I couldn't make sense of the proof in Brion. Sorry about that, in Brion. And so I found, thankfully I found an alternative in Milne, which is very simple. You take a left invariant derivation, then using this rule, you can write, first you can just write that, because by the Hopf algebra structure of A, this thing is just the identity from A to A. Okay? This is delta here. So this goes from A to A tensor A and then back to A. And now you use the property for the left invariant derivations, and you get which gives identity tensor E composition delta composition D composition delta. Okay?
So again, this condition that you wrote in the brackets below,
yeah,
is just the co-version of multiplication by the identity, by the conversion of what it says is M multiplication of X times E is equal to X.
Yeah, so this is the mirror property of the identity. Yes. Okay. So we have that, and this just shows that this thing here, which is the evaluation of D on E, this thing determines D, this D determines E. Okay? So, in particular, this map is injective. This is one thing. And on the other hand, given for the converse, given a derivation from A to K, aka an element of the tangent space at E, if the derivation is such that it is zero on the maximal ideal defined by E, then we define define that, and then show that this is a left invariant derivation of A, for which the evaluation map is D.
Again, sorry to interrupt all the time, but because it's I think it would be just useful, because these formulas look weird, to just, maybe as an exercise, or us to try to rewrite that bottom line in terms of an action. So what you would have, this implication, D belongs in derivations, then what this means is that, you can write it if you want, D of X, what this says is D of X is equal to D of X times E
times E. Yeah.
And then this is equal to E times D of X.
Okay.
Multiplication of D at E, yes, okay, so this is important to just understand that this is all that there is. And this is because D is invariant under the action of G, which means it's a homomorphism of modules. So you can take out the group element. Okay. These weird conditions always translate to something very simple in terms of if you think of them as groups and you think that invariant derivation means it's just a homomorphism of modules. It's an invariant map.
Okay.
And then similarly you can do the same for all the other formulas every time. I'm just saying because these look weird because it's in terms of the co-actions.
Okay, yeah.
But if you think of them in terms of actions, what happens with groups, or with algebras, representations of algebras, it's a very simple formula. Okay?
Okay. Okay, so this is, to me this proof was way simpler than what was in Brion, although what was in Brion was in terms of actions and not in terms of coactions. But I got lost with too many variables, I have to say. Okay, so yeah, it's just the translation of what happens in the action context. Anyway, now there is a proposition that for P is equal 0, every group scheme is reduced. But I think that, I don't know, at some point, okay, let me do that, and then we can discuss some equivalent definitions of for the strictly algebra structure of a tangent space, and this is all that there is from this part of the book. So, theorem actually. If P equals 0, the characteristic, then every group scheme is reduced.
I.e., it's a group.
It's a group, yeah.
It's just a group, just a finite group.
It's a body. So the exercise for you is to find where we use the assumption P equals 0, because I don't know. Anyway. Okay, let G. Suppose that G is local, is so infinitesimal. With maximal ideal M of the coordinate ring, we will show that it is trivial. We will show that G equals T. Actually, given the proof, I think that we need finite here. Yeah, because
everything we do is finite.
Okay.
Finite is everything we do is finite.
Okay, because we consider that A has a finite dimension.
Always, always.
Okay, okay.
In these notes, everything we do is about finite.
Let me tell you the proof for safety. So, given this proposition, we know that this is a tangent space at the identity, and we know that it has a basis consisting of left invariant derivations, of the evaluations of left invariant derivations. So it has a basis consisting of derivations d1 to dm, okay? Which we suppose that are the dual functionals for some elements a1, am inside the maximal ideal. Okay? Just we pick a basis for this space, whose dual basis is the one given by the derivations. The whole thing of the proof is that given that this dual basis consists of derivations, i.e. linear mappings that satisfy the Leibniz rule, we can define a very large homomorphism from the algebra, the coordinate algebra of A, into an algebra of Taylor polynomials. So, i.e. we have that the derivations on the element E, they are delta I j. Now, define this mapping this is just the formal Laurent polynomial, not Laurent polynomials, the formal power series, sorry, in T1 Tm. And this mapping takes an element A and gives us define this map. And given the Leibniz rule, one can check that this is an algebra homomorphism. Actually, I'm pretty sure that we don't need the di to be left invariant. We just need that they are derivations.
Your DIs are maps from A to A. Or from A to K.
From A, they are from A to K. This thing gives us something in K because it's actually the evaluation of the DIs. It's from A to A and then composition with E. So it's they are the evaluations of the derivations at the element E, which is derivation from A to K. So yeah, they are just derivations from A to K.
I n, 1, I n, what do they depend on?
Right, the sum overall.
No, it's just you take the sum overall of these powers.
Ah, okay.
It's just a composition.
Okay. No.
So, since U is a K algebra homomorphic. Okay? Okay, this is just the difficult part to show, which I won't show, but we can discuss it. But I will explain how from this we get the result. It's okay, just a simple algebra. So, we can see now by this property that evaluating this map at AJ, AI, will give us TI plus higher order terms, always. Higher order terms, which means that it is equivalent to Ti modulo the square mod. Okay? What this does is that when we take the composition, when we take this mapping here, for every finite truncation of this thing, which is the same as the truncation of the corresponding polynomial ring, we have that this we will get a mapping that is surjetic. So we get that, and then we have a surjective mapping here. Okay, this is isomorphic to that, because we have killed large powers in any case. And what we have now is that the image of A inside this thing modulo the only maximal ideal, not the only, the only maximal ideal, the square of the only maximal ideal contains Ti. So it's, I will write it down and it will be simpler. So, U, the image of A in the image of A only maximal ideal of this algebra. This algebra here is a local algebra because we have quotiented with the power of a maximal ideal. The only maximal ideal in this algebra.
And it's important that this is true for all n.
This is true for all n, yeah, for every n.
Isn't that where the characteristic 0 comes in?
Why is that?
Because if you have characteristic 3, some power of this ideal might vanish. Or just return to the original ideal.
If n is p,
Yeah. If n is p, you're right, this has bounded dimension. Oh, yes, you're right. Yeah, okay, so 1 point clarified. I have more questions though. Anyway. Okay. So, very nice. Anyway, the image inside this algebra of A, taking all these compositions, modulo this ideal squared is generated by Ti plus this thing. And if you remember, we had proven a criterion for local algebras saying that if you have a subalgebra which modulo the square of the maximal ideal generates the maximal ideal, then it's the whole algebra. So we have a surjective map from A to every such truncated algebra. Is that all right?
Yes.
I see doubtful faces. To be honest, I haven't grasped the essence of this proof. I mean, I'm pretty sure that this thing corresponds to something geometric. The fact that I don't know how we came up with injecting taking a map of A into the formal power series. It should be something like it's like a Taylor expansion of some function at some point, but I don't know. Yes, actually, this is a Taylor expansion. Okay, this makes a little bit of sense because if A we consider it as functions on a geometric space, then this should be the formal power series of A. And what this says is actually that maybe it means that it's never ending. So it's not a polynomial, it's a pure formal series. For p equals 0,
I mean, depends on what you mean by geometric. This is an analytic proof, and essentially what you show is that it's reduced so that it has no nilpotence, more or less.
Okay.
It's algebraic / analytic, I don't know. I don't know what kind of intuition. I don't see something more intuitive, to be honest.
okay. Yeah, it's analytic.
Because the notion of reduce. Okay, how do you think about the
step by step, it is clear to me. For this part here, because I haven't done the calculations for why this is actually a homomorphism, but I think that we don't need the derivations to be left invariant. I don't know how we can use it. It's just that we have derivations.
You can define the map, but then it will probably not be surjective. It will not contain the power of the maximal ideal being in the kernel. That's what you do, right? Essentially.
Yeah.
You want the Ti's to the N to be inside the kernel of U.
But I mean, in any case, we can choose the DI to be derivations from A to K by definition of, we have shown that this is actually isomorphic to the derivations from A to K. We can choose a dual basis, DI, such that DI of AJ equals delta IJ. So the problem would have to be that this map is not a homomorphism for DI derivations chosen like that in general. So they must come from derivations of A for some reason. So I speculate that the only thing that we need is that the vector fields of A map surjectively onto the tangent space. Maybe that should be. Anyway, this part needs clarification by means of calculation. Okay? But the important part is that I understood yesterday that I don't know why it only works for P equals 0. So yeah, these dimensions here are bounded if P is positive. Okay? So to conclude, the dimension of this thing goes to infinity as n goes to infinity. So if n greater or equal than 1, the dimension of K so necessarily A is K if we consider A local. Okay? Anyway, the whole thing is that such a map exists. If this map exists and is a K alpha homomorphic, the rest is just weird stuff happening with the composition. Not possible stuff. Okay. Anyway. So in characteristic 0, every group finite group scheme is a group. And now it's just, I have just a discussion, a little bit of a discussion. So to recapitulate. The tangent space of a group scheme at the identity, which we define to be the Lie algebra of G, has a restricted Lie algebra structure. Okay? Recall that restricted means that it's not only a Lie algebra, but it has a Pth power mapping inherited by the isomorphism by this isomorphism here. Okay? Now, for a mapping, for a homomorphism of group schemes F, we know that dF at E defines a mapping between the tangent spaces. We call that mapping Lie of F, and it's actually a homomorphism. It's actually a homomorphism of restricted Lie algebras. And why that is, I think, needs a little bit of a discussion on the equivalent ways to define the Lie algebra structure of a tangent space. So to me there are many.
The subscript df is the at EF.
Ah, yes. Sorry. Okay. So we have a homomorphism between two group schemes, a homomorphism between two vector spaces, which are at the same time restricted Lie algebras. But the structures that they have is that one is isomorphic to the G invariant derivations in G, the other is isomorphic to the H invariant derivations on H. So why do these two structures happen to be the same? This is the thing. Why is the pth power mapping the same? Okay, first of all, if we really look at it as we have an action on the derivations on G and an action on the derivations of H, and then F is an equivariant mapping, then it's normal that it is the algebra homomorphism. So this is one thing. The other way to obtain this structure, which I won't prove, but Milne says it's an easy exercise to do, is that we have a natural way of embedding the tangent space of G in a Lie algebra GL of itself actually, and this is where the restricted Lie algebra structure comes from. So equivalent definition of restricted Lie structure on the tangent space of E. We have, by conjugation, G acting on itself. Fixing the identity element. Okay? And this thing gives an action of G on the tangent space at E.
Okay. Which is the adjoint representation.
Yes. This thing is exactly the adjoint representation of G into GL of this tangent space, and then taking the differential of that, the adjoint at E, this gives an embedding of this tangent space. I don't know if it's actually an embedding. It's not an embedding necessarily. This can very well have a kernel, I guess, the adjoint representation.
Yes.
Yeah. So it's not an embedding, still it's a mapping into the GL of PEG, which is a tangent space of the general linear group at the identity. And okay, we define in this way TE of G obtains a Lie bracket and a pth power mapping. Okay? The thing is that this construction is functorial in G, so it's given that, having shown that this definition definition of the restricted Lie algebra on G is equivalent to the one that we did before, it's very easy to see why, given a homomorphism of group schemes, we get a homomorphism between the Lie algebras, because this construction is factorial. You take G8, homomorphism between them, and then some natural construction mapping the tangent spaces into corresponding Lie algebras, and it's all equivariant.
So 90% of all that is classical in the sense it's exactly what you do with Lie groups. So
yes,
we are not differential geometers, but if we had someone, then it would be something that you might also learn in an undergraduate course in differential geometry. The only extra information is the P-restricted structure,
yes,
which is the characteristic P, which is philosophically that, you know, algebraic geometry is differential geometry characteristic 0, and interesting phenomena happen only in characteristic P in general.
And
so all of that is something that the adjoint representation and so on is something that you do for Lie groups. If we had seen it, it's somehow classical. The only extra is characteristic P phenomena.
yeah. And the P-restricted structure is something that encodes the group action as well, because
yes. And this is why these group schemes are very interesting, is because characteristic P is interesting in algebraic geometry because it's not covered by differential geometry, but it's also interesting because in characteristic P you have phenomena of modular representation theory that you don't have in characteristic 0. So somehow they are the two interesting aspects of characteristic P combined, non-trivial differential geometry, non-trivial algebraic geometry, and non-trivial representation theory that we will see probably next week.
yeah. So in the end, it's F is naturally a homomorphism, actually, Lie of F is naturally a homomorphism of restricted Lie algebras. Anyway, essentially this is all concerning the definition and the basic properties of the Lie algebras on the group scheme. I think there is room for a lot of discussion here. For example, there are more equivalent definitions. Actually, for me to formally define this representation is kind of, I mean, I write that, okay, this is something by codification, fixing E. What does fixing E mean? And again, how do we get that representation? Because this is actually, yeah, all that I need, it needs formalism to be more strict. Also, this embedding as well. Because to have this embedding, this must mean that we see that as a group scheme, no? Yeah. And we should see that as a kind of functor as well, which is in Milne. So G, I think, or the tangent, yeah, actually in Milne I saw that he defines the tangent space to be the functor taking R to the fiber of G of R of epsilon over G of R.
Yeah, okay, this is geometric, okay.
Yeah.
But I guess you're done with the algebras and we will talk about Frobenius
yes.
next.
We can, but I'm saying that there is room for many clarifications here. So we can have a break.
Because I think Frobenius is exactly what we're talking. It's a phenomenon in characteristic P which is important, whereas this is more or less something really classical that if one has questions we can check it in the literature, whereas the characteristic P phenomena are very special in this topic. Let's take 10 minutes.
Yeah. Άλλο τόσο, ξέρω, καμιά ώρα, θα φροντίσω να τελειώσω δηλαδή.
Πώς, δεν μπορώ να μπω, είναι κλειδωμένο. Θα το κατεβάσω να δει μας βλέπει, θα μας ακούει. Εντάξει, θα το κόψω.